So numerical number 6, assignment number 5. Calculate the mass of benzene that should be added to a solution containing 1 mole of benzene and 2 moles of toluene so as to increase the vapor pressure of solution by 30 millimeters. Vapor pressures of pure benzene and toluene are 150 and 60 millimeters respectively. So we'll first calculate the initial vapor pressure of solution. So this will be PS is equal to P naught benzene is 150 into mole fraction is 1 by 3. P naught of toluene is 60, mole fraction is 2 by 3. So this will come out to 90 millimeters. Now, we want to increase vapor pressure by 30 millimeters. For that, how much benzene should be added? Say, number of moles of benzene added is equal to X. Best is assume number of moles to be added. If you start with mass added, then calculations will be complicated. So this will be new vapor pressure will be 90 plus 30. So this will be 120 will be equal to 150 into new mole fraction of benzene will be 1 plus X divided by 3 plus X. P naught toluene into new mole fraction of toluene will be 2 divided by 3 plus X. Calculate the value of X. This will come out to 3. So 3 moles of benzene should be added. So weight of benzene added will be 3 into molecular weight. So many grams of benzene should be added. Numerical number 7. Calculate mole fraction of A in the vapor phase above the solution prepared by mixing 31.2 grams of A and 110.4 grams of B. Molecular weights are given. Vapor pressures of pure A and B are 80 and 40 millimeters respectively. We'll first calculate number of moles. So number of moles of A will be 31.2 grams divided by molecular weight 78. This is 0.4. The other one is 110 grams, 110.4. Number of moles of B will be 110.4 divided by molecular weight 92, 1.2. Now, first we'll calculate P naught A and P naught B. PA and PB. PA will be P naught A 80 into mole fraction of A will be 0.4 divided by total 1.6. This will come out to 20 millimeters. Similarly, PB will be P naught of B is 40 millimeters. 40 into mole fraction of B will be 1.2 divided by total. This will come out to 30 millimeters. It means vapor pressure of solution will be sum of these two, 50 millimeters. We have to calculate vapor pressure of A in the vapor phase. So I'll use the formula PA is equal to PS into YA. So mole fraction of A in the vapor state will be PA, that is 20, divided by P solution 50.4 is the answer. Right? Now coming to numerical number 8. Calculate vapor pressure of the solution containing equal number of molecules of liquids A and B. See, if there are equal number of molecules of two components, it means number of moles will be equal. If number of moles are equal, it means mole fraction will be equal. So mole fraction of A is equal to B is equal to 0.5. So this you have to write when you write that in the when you solve in the examination. So that what I've told you, mole fraction of A and B will be 0.5 each. The rest will be very small numerical, simple numerical. P solution will be P naught A 270 into mole fraction 0.5 plus P naught B is 130 into mole fraction is 0.5. That's it. Numerical number 9. Calculate mole fraction of A in a solution of A and B whose total vapor pressure is 115. P naught A and P naught B values are given. So P total is 115, yani vapor pressure solution. P naught A is 160 into mole fraction of A. P naught B is 100 into mole fraction of B will be 1 minus chi A. Calculate the value of chi A, that will be the answer. And according to the sheet, it is 0.25. Last numerical. Vapor pressures of pure liquids A and B are 450 and 700 millimeters respectively. Calculate mole fraction of A in the solution and in the vapor phase if total vapor pressure of the solution is 600 millimeters. See, we are given P solution 600 is equal to P naught A is 450 into mole fraction of A, I'm writing chi A. P naught B is 700 millimeters into 1 minus chi A. Calculate the value of chi A. This will come out to 0.4. From this, we can find out the value of PA. PA will be 450 into chi A, 180 millimeters. Remember, this is one answer. This is mole fraction of A in the liquid phase. So PA is 180 millimeters. Now again, PA is equal to P solution into YA. YA will be PA 180. P solution is 600 millimeters. So this will be 0.3. These are two answers. Now coming to theoretical questions, there are two theoretical questions. Out of 1 molar and 1 molar solutions of the same solute, aqueous solutions, remember aqueous has a purpose here. Which solution is more concentrated and why? 1 molar, 1 molar. See, you'll have to explain in your own words. See the explanation. In both the solutions, there'll be 1 mole of solute. This 1 mole of solute is present in 1 liter of the solution. And this is present in 1 kg, or I can say 1000 cc of water, right? 1 kilogram of solvent. Solvent is water. Now here, total volume of solute and solvent is 1000 cc. Whereas in this case, only the volume of solvent is 1000 cc. It means in the first case, volume of solution is 1000, means volume of solvent will be less than 1000 cc. So 1 mole of solute present in less than 1000 cc of water. In this case, 1 mole of solute present in 1000 cc of water. That is why this solution will be more concentrated than 1 molar solution. Second question is, why can't we obtain pure ethanol by fractional distillation of ethanol containing some water? Because ethanol and water, they form azeotropic mixture and they distill together as at a constant boiling point with constant composition due to hydrogen bonding. So in short, you can write due to formation of hydrogen bonding and azeotropic mixture. Children, today we are going to finish the chapter and there will be plenty of numericals, plenty of modification in equations which I gave you earlier. Right on. Next topic is abnormal molecular weights. Abnormal molecular weights. You know, molecular weight of sodium hydroxide is 40, but experimentally, if I determine molecular weight of NaOH and it comes out to say 20, less than 40 or more than 40, then I'll say that the value which I've determined is an abnormal value. Remember, all colligative properties, they can be used to determine molecular weight of solute, but sometimes molecular weight which we determine is either less or more than the actual value. Naturally, that would be called abnormal molecular weight. We're going to study what are the reasons for obtaining abnormal molecular weight. Right on. All CPs, all colligative properties can be used to determine molecular weight of solutes, molecular weight of non-volatile solutes, NV solutes. So, if molecular weight determined on the basis of a colligative property is less or more than the actual value, it is called abnormal molecular weight. It is called abnormal molecular weight. Reasons for obtaining abnormal molecular weights are, now relax for a while. I'll explain these two reasons. After I've fully explained, then only I'll start dictating you. It's a very, very important topic. See, I gave you the definition of colligative properties where I said colligative properties are those which depend on the effective number of non-volatile solute particles. At that time, I said effective number. These two words you'll be able to understand after maybe 2 classes. And the time has come, we'll be using those 2 words, effective number. Look here. Let us say we dissolve X molecules of urea in Y grams of water and elevation in boiling point is 2 degrees centigrade. Don't write anything, just understand. Say we dissolve X molecules of urea in Y grams of water and the value of elevation in boiling point is 0.2 degrees centigrade. We dissolve X molecule of glucose in same amount of water. Elevation and boiling point will be same because the definition of boiling point says that colligative property, value of colligative property will depend on number of solute particles irrespective of their nature. It means whatever be the solute, value of colligative property will remain the same provided number of solute particles is same and obviously solvent is same, amount of solvent is same. That is quite obvious. It means if I dissolve same number of molecules of sugar in same amount of solvent, elevation should be 0.2. If I dissolve same number of molecules of NaOH in same amount of water, again I expect, as usual, I'll expect that the value of elevation should be 0.2, but in this case, value of elevation will not be 0.2, it will be 0.4. Now, what is the problem in the fourth case? In first 3, it was same. How come the value of property is double in the second case? See, in first 3 cases, in first 3 examples, solute is a covalent compound. When dissolved in water, covalent compounds do not ionize, they do not undergo any change. But when NaOH is dissolved in water, one molecule will ionize, will split into 2 ions. It means if I dissolve 100 molecules of NaOH in water, it will change into 200 ions. So there will be no NaOH molecule in the solution. There will be rather effectively 200 particles. This is the meaning of effective number. Effectively, 100 molecules of NaOH will be 200 particles. Since number of effective particles is doubled, value of colligative property will be doubled. right? Naturally, if I dissolve same number of molecules of barium chloride, then one molecule will give 3 ions. Number of effective particles will increase 3 times. Value of colligative property will be 3 times. It will not be 0.2, it will be 0.6. Now I take another case. Let us say the solvent is benzene. Elevation is expected, let us say 0.2, 0.2. If I dissolve X molecules of a carboxylic acid, any carboxylic acid in benzene, again I expect that the value of elevation should be 0.2. In the first and second case, value is same, but in the third case, value is half of it, 0.1. The reason is when carboxylic acids are dissolved in non-polar solvents, non-polar like it may be any alkane, it may be benzene, toluene, or any aliphatic hydrocarbon, 2 molecules of acetic acid or any carboxylic acid will join together and form a dimer. What is dimer? Combination of 2 molecules. So if I dissolve 100 molecules of any carboxylic acid in benzene, it will lead to the formation of 50 dimers, aggregates of 2 molecules each. So since number of effective particles will be reduced to half, value of colligative property will also be reduced to half. Remember, all colligative properties are inversely proportional to molecular weight of solute. Like in this case, colligative property is halved, molecular weight will be double than the expected. In case of ionic compounds like NaOH, I expect that the molecular weight should be 40, but since colligative property doubles, value of molecular weight calculated will be half, that is, it will be 20, will not be 40. So these are 2 reasons. One reason is called dissociation of solute, that is ionization. The other is called association of solute, right? Now I'm dictating you continuously for quite some time. Right. Reasons for obtaining abnormal molecular weights are: number 1, dissociation of solute. Dissociation of solute. Right. When ionic solutes are dissolved in water, they ionize into 2 or more ions. Due to this, effective number of solute particles increases and the value of Cp increases. Value of Cp increases. Since all Cp's are inversely proportional to molecular weight of solute, from a calculated molecular weight is less than expected. For example, when NaOH is dissolved in water, each molecule ionizes to give 2 ions, so that effective number of solute particles is doubled value of Cp is doubled and calculated molecular weight is 20 rather than 40. Is 20 rather than 40. Number 2, second reason. Association of solute. Some covalent solutes, when dissolved in a non-polar solvent like benzene, join together to form dimers, trimers, etc. Dimer combination of 2 molecules, trimer combination of 3 molecules, pentamer combination of 5 molecules. Similarly, you know the term polymer. Polymer is many. Combination of many molecules, we call it polymer. Due to this, effective number of solute particles decreases value of Cp decreases and the calculated molecular weight is more than expected. For example, when carboxylic acids are dissolved in benzene, 2 molecules join together to form a dimer due to hydrogen bonding. Draw the structure of the dimer. How the dimer is formed? Draw this. These are 2 molecules of carboxylic acid, RCOH. Look at the polarity of bonds. Oxygen is more electronegative than carbon, also more electronegative than hydrogen. So this is formation of hydrogen bonding between 2 molecules of carboxylic acid. 2 will join together and exist as one particle called a dimer. Yes, further write down. Due to this, effective number of solute particles is halved, value of Cp is halved, and calculated molecular weight is doubled. So remember, if we determine molecular weight of acetic acid by dissolving in benzene, by of course using one of the colligative properties, then molecular weight of acetic acid will come out to 120 rather than 60. Now, we have solved so many numericals on these 4 colligative properties in past 2-3 days. If value of colligative properties were wrong, then calculated molecular weights should also have been wrong. See, In the past, whatever numericals we solved, in those, for those solutes, there was neither association nor dissociation. There was neither association nor dissociation. But in future, we will consider mixture of this type of solutes. Some may undergo association, some may undergo dissociation, some may neither undergo association nor dissociation. In that case, how do we calculate actual molecular weight, accurate molecular weight? For that, I'm introducing next topic, right on vant Hoff's factor. Small v, vant Hoff's factor. Symbol for vant Hoff's factor is I. This is defined by following ratios. This is defined by following ratios. I'm giving you three ratios. These three ratios are the definition of I, that is vant Hoff factor. What are these definitions? I is equal to normal molecular weight divided by calculated molecular weight. If I say calculated molecular weight, means calculated on the basis of Cp, right? Second definition, effective number of solute particles divided by actual number of particles. Actual number of particles dissolved, you can say. Third definition will be experimental value of colligative property, right? And denominator will be expected value of colligative property. Expected value of colligative property. These three definitions I'll explain by writing something on the right hand side. I think there's no need to write what I'm explaining on the right hand side of these three ratios. For dissociation and for association. Let us say we take the case of dissociation. If you think, recall, I gave you the example of sodium hydroxide. Normal molecular weight of NaOH is 40, and on the basis of colligative property, it should come out to 20. It means value for NaOH, value of I for NaOH should be 2. Second definition, effective number of solute particles divided by actual. Actually, I dissolved X number of molecules, but on ionization, they became double, 2x. Value of I for NaOH is 2. Third, I was expecting that the elevation and boiling point should be 0.2, but it came out 0.4. It means 2. So one thing is clear, if there is dissociation, value of I will be more than 1. Not only more than 1, if dissociation is 100%, then value of I will be equal to the number of ions produced by one molecule. Think, if it is barium chloride, one molecule will give 3 ions, value of I will be 3. If it is ammonium chloride, one molecule will give 2 ions, value of I will be 2. So whatever is the number of ions produced by one molecule, that will be the value of I in case of dissociation, provided dissociation is 100%. If it is not 100%, then we'll take up another topic today. Now, association. Which example did I take? Carboxylic acid dissolved in benzene. Calculated, I'll take the example of acetic acid. Normal molecular weight of acetic acid is 60. It comes out to be double, that is 120. Value will be 1 by 2. Effective number of solute particles. I dissolved X molecules of acetic acid, but those X molecules converted into X by 2 dimers. Right? 100 molecules, they converted into 50 dimers. Value of I is again 1 by 2. I was expecting that elevation in boiling point should be 0.2, but it came out to 0.1. So conclusion is, number one, value of I will be less than 1 in case of association. Second conclusion is, if association is 100%, then value of I will be 1 divided by how many molecules join to form aggregate. If 2 molecules join to form the aggregate, that is dimer, 1 by 2. If 5 molecules join to form one aggregated particle, it will be 1 by 5. What do we call it? Pentamer. If trimer is formed, value of I will be 1 by 3. Right? Now start writing. For dissociation, I is more than 1. And for association, I is less than 1. Further item. If dissociation is 100%, then I is equal to number of ions formed by one molecule. For example, for NaCl, I is equal to 2. For Na2CO3, I is equal to 3. Next paragraph. For complete association, I is equal to 1 divided by, in the denominator, you are going to write almost one sentence. So I is equal to 1 divided by number of molecules which join together to form an aggregate. For example, for dimer formation, I is equal to 1 by 2. For tetramer, I is equal to 1 by 4. Now, how are we going to use this value I? Remember, this I will be used as a correction factor to calculate accurate molecular weight of the solute. If solute undergoes association or dissociation, that abnormality in the calculated molecular weight will be cancelled and we will get accurate molecular weight by using the value of I. How do we use that? Right on. I is used as a correction factor in equations for CPs, for colligative properties, to calculate accurate molecular weight of solutes so that equations for CPs are modified as follows. So we studied 4 colligative properties. In all colligative properties, there were, I think, minimum 2 equations, 2 or more equations we studied in every colligative property. All those equations will be modified. On the right hand side, we'll be using I, so that abnormality is cancelled. Right on. Number 1, relative lowering of VP. Relative lowering of VP. Right on. For 1 mole of solute, for 1 solute, equation 1A becomes P naught A minus PS divided by P naught A is equal to, earlier it was chi B, now it becomes I into chi B. This is modification of equation number 1A, therefore numbering is 1A dash. Further write down, for more than 1 solute, equation 1C, not B, equation 1C becomes P naught A minus PS upon P naught A is equal to, earlier it was sum of the mole fractions of all non-volatile solutes. Now it becomes I1 mole fraction of solute 1 plus I2 mole fraction of solute 2 and so on. Look at the right hand side. We multiply mole fraction of each solute by vant Hoff factor of that solute and then add them. So this becomes equation 1C dash. There were 2 equations, 1B and 1D also. Right on. Equation 1B becomes P naught A minus PS upon PS. There was slight, this is not very frequently used. P naught A minus PS upon PS is equal to, earlier it was NB divided by NA. Now it becomes I into NB divided by NA. 1B dash. Last, equation 1D becomes, 1D was for more than 1 solutes. So 1D becomes P naught A minus PS upon P naught PS is equal to I1 NB1 plus I2 NB2 and so on, divided by Na. What's that? Number of moles of solute multiplied by vant Hoff factor of that solute, added for every solute like this, divided by number of moles of solvent. So this becomes 1D dash. Now, based on this, we'll solve one numerical. I'm sharing on WhatsApp and chat box also. You see, this is numerical number 32. Yes, you can check. So the numerical is calculate lowering in vapor pressure of solvent in the solution containing 20.6 grams of sodium bromide. I'll calculate number of moles. Number of moles of NaBr will be 20.6 divided by molecular weight as 103. So number of moles will be 0.2. 14.2 grams of sodium carbonate. So sodium sulfate. So number of moles of sodium sulfate will be 14.2 divided by molecular weight 0.1, dissolved in 534.6 grams of water. Number of moles of water will be 534.6 divided by molecular weight 18. I'll tell you this will come out to 29.7. Now we have to calculate lowering in vapor pressure. P naught of water is given 300 millimeters. So P naught A minus PS divided by P naught. Numerator is lowering in vapor pressure. So numerator will be the answer. Is equal to, we'll have to add mole fractions of both the solutes. Mole fraction of NaBr will be 0.2 divided by total 30 plus mole fraction of sodium sulfate 0.1 divided by 30. So this numerator will be the answer. I'll tell you this will come out to 7 millimeters. Right, 7 millimeters will be the lowering in vapor pressure. Now, second colligative property, modification in second colligative property. Remember, second and third colligative properties had similar mathematical expressions. So modification, of course, has to be done, but numerical will take only one numerical for both these properties. Number two, elevation in boiling point. Elevation in boiling point. For one solute, equation 2a becomes delta TB is equal to I into KB into molality. Molality will be WB by MB into 1000 divided by WA. This is for one solute. For the write down, for more than one solute, equation 2C becomes, not 2B, 2C becomes, delta will modify and write it 2A dash. Delta TB is equal to I KB number of moles. Wait a minute, sorry. Number of moles of all the solutes will be added and it will be I1 into NB1 plus I2 NB2. As I told you earlier, number of moles of each solute multiplied by its own I factor and will be added into 1000 divided by WA. You can label it 2C dash. 2C dash. Now, third colligative property, modification in third colligative property. Pattern number 3, depression in freezing point. Depression in freezing point. For one solute, equation 3A becomes exactly similar equation. 3A becomes, the only difference will be in place of KB, it will be KF. I in delta TB is equal to IKF into molality and we'll label it as 3A dash. Take your time to note it down. Don't leave it to the video. Further write down, for two or more solutes, equation 3C becomes, yes, note down this one. I made a slight change. In place of Kp, I've changed it to Kf. That is the only change. So equations are similar. So we'll take up only one numerical for this. You copy this equation. In the meantime, I'm sharing numerical. On WhatsApp, I think it has been shared 2 times that you can make out yourself. Okay, I'm solving it. Calculate boiling point of the solution containing 5.3 grams of sodium carbonate. Okay, I'll substitute together. And 5.85 grams of NaCl dissolved in 200 grams of water. Kb of water is 0.52. So delta Tb will be equal to Kb is 0.52. 5.3 grams of sodium carbonate. Please be very attentive whilst I'm solving this numerical. For sodium carbonate, value of I will be 3 because one molecule will split into 3 ions. So 3 into number of moles will be 5.3 divided by molecular weight, 106. For NaCl, N factor, for NaCl, I will be 2, number of moles will be 5.85 divided by 58.5 into 1000 divided by weight of solvent, 200 grams. So when you calculate, this will come out to 0.91. So boiling point of solution will be 100.91 degrees centigrade. 100.91 degrees centigrade. Now coming to fourth and the last colligative property. After that also we have a lot of work to do, but we'll finish today. Number 4, osmotic pressure. In osmotic pressure, I gave you 4 equations. All the 4 will be modified now. Tada. Equation 4a becomes pi is equal to IMRT. Earlier it was pi is equal to MRT. Now it becomes IMRT. 4a dash. Equation 4b becomes, earlier it was pi b is equal to NBRT. Now I into NBRT. Third equation was when there are 2 or more solutes. Right on. Equation 4c becomes pi b is equal to I1 NB1 plus I2 NB2 and so on. This part becomes this into RT. And last equation, that an equation 4D becomes equation 4D. Equation 4D was when there are 2 solutions of different molarity. That one, pi is equal to I2 into M2 minus I1 into M1 into RT. Earlier it was M2 minus M1 into RT. Remember, product of I and M, higher minus lower, is kept in this bracket. I into M, higher minus lower, because value of Cp will always be positive. One numerical on this. This is numerical number 34. We have solved so many numericals. 34th now. Yes. Numerical is calculate the mass of sodium hydroxide present in 1 liter of an aqueous 1 liter of an aqueous solution, which also contains 6 grams of urea and exerts OP of 8.21 atmospheres at minus 73 degrees centigrade. See, pi is 8.21, volume is in 1 liter of solution is equal to, now there are two solutes. One is NaOH. For NaOH, I is 2, weight we have to calculate. I is 2, weight we have to calculate, plus urea. For urea, I is 1, number of moles will be 6 divided by 60 into R into temperature. Minus 73 will be 200 Kelvin. I hope you are able to read. I'll read it for you. 0.0821 multiplied by 200 is the temperature. So this W will be the answer. This will come out to 8 grams. This is the answer. Now remember, when you're solving any numerical on colligated property, always use these modified equations. Always get used to vant Hoff factor. Use these modified equations only. If there is neither association nor dissociation, then the value of I will be 1. Right? Like in this case, urea neither undergoes association nor dissociation. Value of I substituted equal to 1. Whereas NaOH dissociates into 2 ions, I've used the value of I. Now, last topic is that if dissociation is not complete, if dissociation or association is not 100%, then what will be the value of I? In that case, if you remember, there was a topic in equilibrium in 11th standard, degree of dissociation. So we'll use that type of concept now. Right on. Next topic, next heading is vant Hoff's factor and degree of dissociation or association. You know the symbol for vant Hoff factor I, and for degree of association or dissociation value symbol will be alpha. That for dissociation, alpha is defined as, alpha means degree of dissociation, is defined as the fraction of total number of molecules or moles of solute which dissociate into ions. Next paragraph. for partial dissociation, I and alpha are related to each other as given below. I is equal to I minus 1 divided by n minus 1. Label this. What is this n? N is equal to number of ions produced by one molecule of solute. I've shared one numerical on WhatsApp and this chat box also. We'll solve one numerical on this. See, numerical is 0.2 molar solution of an ionic solute AB2. Ionic solute AB2 means one molecule will give 3 ions. It means in this equation, which I just now rubbed, value of n will be 3. One molecule will give 3 ions. Exerts an OP of 7.2 bar at 27 degrees centigrade. Calculate percentage dissociation of solute. Now, we'll calculate the value of I. Pi 7.2 is equal to I into molarity 0.2 R. Pressure is on bar scale. So this will be 0.083 and temperature is 27 means 300. We'll calculate the value of I. Remember, since this is the case of dissociation, value of I will always be more than 1. In case you calculate, but it comes out to less than 1, it means there's something wrong with your calculation. You must check it. So this I will be 1.4458. Now, alpha is equal to I minus 1 divided by n. Number of ions produced by one molecule will be 3. N is 3 minus 1. Right? To calculate the value of alpha, alpha will be 0.2229. Also remember, alpha will always be less than 1 because this is by definition fraction. 22.29%. So degree of dissociation is 22.9%. Now, almost towards the end. Next paragraph. For association, alpha is defined as the fraction of total number of molecules or moles which associate to form aggregates. Next paragraph. For partial association, I and alpha are related as follows. Pattern alpha is equal to I minus 1. There's no change in numerator. Denominator will be different, divided by 1 by n minus 1. Now in this case, what is n? Write on n is number of molecules which join together to form one aggregated particle. To form one aggregated particle. Now the last numerical, and with that we'll finish the chapter as well. I'm sharing the numerical. Yes. Numerical is a solution containing 4.8 grams of solute X, molecular weight 60, dissolved in 600 grams of benzene, shows a depression in freezing point of 0.55 degrees centigrade. Kf of benzene is this much. Calculate percentage association. Solute forms dimer in the solution. So this will be depression is 0.55 is equal to I. We have to calculate. Kf is 5.12 into molality. Now molality will be 4.8 grams of solute, molecular weight 60 into 1000 divided by weight of solvent. There's the weight. It is 600 grams. We'll calculate the value of I. Since this is association, value will be less than 1. This will be 0.8056. This is the value of I. Now we'll calculate the value of alpha. For that, we'll use the relation which I gave you. Alpha will be I minus 1 divided by, for dimer formation, value of N is 2. So it will be 1 by 2 minus 1. So when you calculate, alpha will come out to 0.3888. So association will be 38.88%. So children, with that, we finish this chapter. In the next class, that is on Thursday, we'll start with organic chemistry. Organic is too lengthy in 12th standard. There are 4 long chapters. It will become monotonous if we keep on doing organic. What I'll do is I'll complete 2 chapters of organic chemistry, which will take not less than 2 months. 2 chapters. After 2 chapters of organic, we'll take 1 chapter of physical chemistry just for a change, and then again go back to organic chemistry. Please keep on. One thing is disappointing. Nobody is asking me to share more and more MCQs, because in the initial sheets, MCQs were easy. Later, in subsequent sheets, MCQs will be more and more difficult. Sometimes I forget to share, but nobody is asking me to share sheets, and hardly 1 or 2 children ask me doubts on that. Please solve them, and I'll share the next sheet only if someone asks me to share. I'll not share otherwise. You should ask for that. Right, children? Bye, and ask me if there's any doubt. You can call me. Right.